I want to spend this lecture talking about connectivity in graphs, as well as algorithms to test whether a graph is connected, and if it's not connected, to find its connected components. Now, we actually already know about this stuff. So we've talked about what it means for a graph to be connected way back in lecture 22. We gave a definition of a connected graph and what connected components are. And since then, since we've been talking about graph traversals, we've actually already seen that graph traversal algorithms can help us evaluate connectivity. So for example, we already know that if I start a graph traversal algorithm like DFS or BFS on some vertex in an undirected graph, that traversal is guaranteed to visit all of the vertices in the same connected component as my starting point. Which means if I want to know the connected components of my graph, I could do so by running a bunch of traversals. And additionally, if I want to test whether the entire graph is connected, well, I could just run a traversal at some arbitrary starting point and check whether it reaches all of the vertices of the graph. So we have quite a bit of a head start as far as discussing algorithms for connectivity. On the other hand, there's a bit of an elephant in the room, which is, what about directed graphs? And every time we've been discussing components or connectivity so far, and directed graphs have come up, I have refused to talk about the subject further. I've said that's complicated, we've got to spend a whole lecture on that. Well, I guess it's time to do that. So we're going to spend most of this lecture talking about how we can apply our definitions of connectivity to the case of a directed graph. And also, near the end of this lecture is where I think that we make the leap from introductory graph algorithms to intermediate graph algorithms. And I think that when you see the algorithm in question, you will agree that that's a pretty clear, that we're definitely crossing that bridge. So hold on to that thought for near the end of this lecture. In the meantime, what is connectivity again? So an undirected graph is connected if, when I choose any pair of vertices u and w, it is the case that w is reachable from u. Now, one thing I want to observe right off the bat, because I'm going to use this phrasing repeatedly in this lecture, is there's a weird quirk of, I don't know, like English phrasing happening here. W is reachable from U. Just remember here, W is actually the destination in this phrasing. This is saying that I can get from U to W when I say W is reachable from U. So keep that in mind. It's sort of phrased in a weird reverse way. Now, back in lecture 22, when I described what reachability was, I defined reachability in terms of paths. There are lots of equivalent ways of defining reachability, though. Let's choose two vertices. So there's vertex B. Let's choose vertex Q as the other end. So for a graph to be connected, it must be the case that if I choose any two vertices, like B and Q, that one vertex is reachable from the other. Now, it turns out that reachability is actually a symmetric relationship. More on that in a minute. But when I say that one vertex is reachable from the other, there are lots of ways of defining reachability. One really basic way of defining reachability that doesn't really serve our interests very well for what we tend to want to do in this course would be to say, okay, well, Q is reachable from B if there's some way that I can set out from vertex B and just wander around the graph, even if I wander aimlessly and have to double back. So suppose I double back from vertex M to vertex L, and then I walk up to vertex K, and then vertex J, and then vertex I, and then vertex H, and then vertex A, and then I double back 2 more times for some reason, and then finally I wander over to vertex Q. If there is some way to start walking at vertex B and end up at vertex Q, even if I wander around aimlessly for a while, well, then that means that vertex Q is reachable from vertex B. The reason why that definition doesn't help us very much, although it's a valid definition, an equivalent definition to the one that we tend to use, is that we tend to want to talk about certificates of reachability. That is, if I know one vertex is reachable from another, sometimes, although not always, but sometimes I would like to prove that to you by showing you. So one way of showing you is to produce a path. And we know that paths aren't allowed to repeat vertices or edges. And so one way of asserting reachability and one way of defining reachability is to say that vertex Q is reachable from vertex B if there exists a path from B to Q. And what I've now produced here is some path from B to Q. If there's some aimless walk from B to Q, there will always be a path. So we can define reachability in terms of paths. An observation I want to make, though, is if we're talking about reachability in the abstract sense, and let's say I'm writing proofs or something, it can actually be sort of annoying sometimes to think about that only in terms of paths. There are actually properties of reachability that we can exploit that don't require us to formally produce a path, even though the fact that one vertex is reachable from another implies that such a path must exist. And I'll talk about that in a minute. It has to do with the fact that paths have such strict requirements, and that sometimes if I'm thinking about paths formally in an abstract sense, it's annoying to have to keep managing all of those requirements. Now, before I continue with this example, I want to observe that in an undirected graph, connectivity or reachability is a symmetric relationship. What I showed a minute ago was that it's possible to get from B to vertex Q, which means vertex Q is reachable from B. But in an undirected graph, I produced some path from B to Q. Because edges have no inherent direction, I am absolutely welcome to wander that same path in reverse order. I can just follow every edge in reverse order, and therefore I can get from Q to B, which means if Q is reachable from B, then B is reachable from Q. It is a symmetric relationship in an undirected graph. The same is not true of directed graphs. We can still define reachability, but consider this case here. So here is a two-vertex directed graph on two vertices U and V. Notice that V is reachable from U, but U is not reachable from V. And so clearly reachability is not symmetric in undirected graphs. Now, before we proceed, I want to follow on to that thought from a minute ago of just being able to treat reachability as a relationship and not have to worry necessarily about always having a bunch of paths to produce to show it. Now, certainly, it's true that if one vertex is reachable from another, there must exist a path, but sometimes we want to reason about reachability without necessarily having all that extra baggage on hand. So I want to talk about the relationship of reachability in the abstract sense, and I want to observe that the reachability relationship in undirected graphs is what is called an equivalence relation. Now, you may have seen equivalence relations before. We've actually exploited the properties of equivalence relations in this course already. So one notable equivalence relation that we've already seen is big theta. So big theta is actually an equivalence relation. You can go and verify to yourself that it meets these three properties. I want to talk about reachability as an equivalence relation. And if you want a point of reference, so if equivalence relations are new to you, just think of the equal sign. So the way I think about equivalence relations is they're a type of relationship that gives us the properties that we take for granted, the comfortable properties of the equal sign, of the equality relationship. So I'll just run through the three core properties of equivalence relations, and we'll use the equal sign as a point of reference. So think about numbers. It is true for any number A that A equals A. That is called the reflexive property or reflexivity. And if I think about reachability in an undirected graph, if I consider some vertex U, remember that when we first defined paths and reachability in lecture 22, I mentioned that it is valid in our definition for a path to have length 0. So what does it mean for a path to have length 0? Well, recall that the length of a path is the number of edges in that path. So basically a path of length 0 is equivalent to me starting at vertex U, doing nothing, walking nowhere, taking 0 steps, and then figuring out where I end up. Well, I just end up back at vertex U, exactly where I started. And because we consider such a path to be valid, and because we define reachability in terms of paths, that means that naturally vertex U is reachable from itself. Every vertex is always considered reachable from itself because if you're standing on that vertex and you do nothing, then you are on that vertex. And so you can reach that vertex from itself, and therefore reachability is a reflexive relationship. Okay, now with the equal sign, what if I know that A equals B? Well, that also implies that B equals A, because the equality relationship is symmetric. It has the symmetric property or symmetry. And the same is true of reachability in undirected graphs. And this is the key thing that makes connectivity in directed graphs a bit of a pain, because we'll see that, I showed a minute ago that reachability is not symmetric in a directed graph. So in an undirected graph, suppose that I happen to know that V is reachable from U. So I can walk along this path from U to V. Well, as I mentioned a minute ago, I am welcome to traverse the same path in the reverse direction to get from V back to U. So if U is reachable from V, V is reachable from U, and vice versa. So reachability is symmetric in undirected graphs. And that is a property that does not apply in directed graphs, although reflexivity does. And our third property, the transitive property, also applies in both undirected and directed graphs. So with the equal sign, suppose that I know that A equals B and that B equals C. Well, with equality, we know that that implies that A equals C, and that is called the transitive property. And the same thing is true in reachability. So suppose I have three vertices, U, V, and W, and I know that I can reach V from U somehow, and I can reach W from V somehow. Well, then, of course, I could get from U all the way to W by wandering over to V, which I know I can reach, and then wandering from V to W, which I know I can reach from there. And that means that W must be reachable from U as well. And in undirected graphs, if I combine transitivity and symmetry, that also tells me that U is reachable from W. Now, a note about why it's nice to think about the reachability relationship in the abstract sense, rather than always having to prove things in terms of paths, because although paths always exist if reachability applies, talking about reachability and binding ourselves to the notion of a path can be sort of annoying. So here's an example of why that's the case. So consider this vertex U, and then over here I have vertex W, and my intention here is to sort of construct the same example that I just did, but with a specific graph. So suppose I have a situation sort of like this. I have a bunch of vertices that connect U all the way to vertex W. And then somewhere in the middle, I branch off and I can reach, if I want to, I can reach vertex V. Suppose that I happen to know that I can get from U to V, and I can get from V to W. All right, so I'm using an arrow here, even though we're still talking about the undirected case, because what I want to do is illustrate transitivity and observe that, of course, the transitive property here tells me that I can get from U to W. And that's it. I can use the fact that reachability is an equivalence relation to assert that I can reach W from U. If I want to talk about it only in terms of paths, I have to do a bunch of extra bookkeeping. And the reason is because I can get some path that takes me from U to V. I'm going to redraw this a little bit just to clean it up a bit. So suppose I can get from U to V using some path P1. And I can get from V to W using some path P2. And in this diagram, the path P1 would be the path that runs from U to V here, and the path P2 would run up like this from V to W. Now there is a path from U to W, but if I want to use the transitive property to find such a path, it's really annoying. Because if I think about the path P1, which is to wander from U all the way down to V here, and then I think about the path P2, well, P2 actually contains some of the same edges as P1. So creating a path from U to W isn't as easy as just jamming together the path from U to V with the path from V to W. I have to do a bit of extra bookkeeping to eliminate the overlap, which is fine. I could do that, but it's a bit of a pain. So it's easier in that case just to use the transitive property of the reachability relationship. We've seen before the extra bookkeeping I have to do to preserve the constraints of paths, the fact that I can't duplicate edges or vertices. Back in lecture 23, I think it was the proof that said that inside of a tree there can be exactly one path between any two vertices. The proof of that property required me to juggle the fact that when I'm talking about distinct paths, they're not disjoint. And that did require some extra bookkeeping. It was fine, but it did require extra bookkeeping. So I'm arguing here that we can reason about properties of reachability without necessarily always having a path on hand. We can use the fact that if one vertex is reachable from another, there must exist some path between them, and we don't necessarily always have to produce that path to show reachability. We can reason about it using the properties of the reachability relationship. Okay, so let's get down to business. So the main objective of this lecture is to develop algorithms for connectivity testing and for finding connected components. So our first task is, given some undirected graph G, just give me a yes or no answer. Is this graph connected? Now, I'll warn you, as I did back in lecture 22, and the slides are going to warn you in a minute, they're always late to the party on these things, that remember, connectivity testing is not actually really that easy. It looks easy to us because if somebody like me, makes you a nice diagram, you can glance at it, and something about your brain is just really good at detecting connectivity in graphs. And so you can glance at this and say, this is clearly a connected graph. Remember that it's not always that easy. That is the diagram doing a bunch of work for you. However, we already know that if I run a traversal rooted at some vertex, then that traversal will visit all vertices reachable from that vertex. And because reachability is a symmetric relationship, and because it's a transitive relationship, if I happen to know that I can reach, let's try vertex G, and let's say, this is not a formal traversal that I'm doing here, so it's sort of in an arbitrary order. Suppose I know that I can reach vertex I from vertex A, and I can reach vertex G from vertex A in an undirected graph. Well, that means by symmetry, I can reach A from G, and it means by transitivity, I can reach I from G, because I can go from G back up to A, and I can go from A back down to I. And so if I run a traversal rooted at any vertex, and I produce the traversal tree, I have a couple of ways that I could reason about this. One way is I could use the properties of symmetry and transitivity to assert that as long as I know that I can reach every vertex from some arbitrary starting point, that means I can reach every vertex from every other vertex, and therefore the graph is connected. Or alternatively, the way I decided we could present it on the slides here is just talking about spanning trees, because we know already the properties of trees. So if there exists a spanning tree of my graph, well, then the graph has to be connected. Well, why do I know that? Because a spanning tree is a spanning subgraph that is a tree. So by being a spanning subgraph, that means it has to include every vertex of my initial graph G. And because it's a tree, well, I know that trees are connected. So if a spanning tree exists of a graph, that means the graph itself has to be connected because one of its spanning subgraphs is connected. So there are a few ways we can reason about it. It turns out, in a sense, that this property is sort of overbuilt as far as we're concerned, because we have quite a few ways of asserting this property because we know quite a bit of theoretical stuff about graphs and trees and traversals by now. So this means that our connectivity test basically amounts to choose a starting point and run a traversal. So if I want to test connectivity of an undirected graph, I just run whichever traversal I want, DFS or BFS, at some arbitrary starting point, and I just test whether I'm able to visit all vertices in that traversal. We know already that this just requires linear time in the number of vertices and edges. This is another great example of being able to use an off-the-shelf traversal. Because I'm just running basic BFS or DFS without changing anything, I don't need to worry about reproving the correctness or the running time. I just get to use those right off the shelf. Okay, so a connectivity test can be done with a simple one round of some traversal. So I guess the next question is going to be, what about if I want to isolate the connected components of a disconnected graph? So here's a disconnected graph, and I mentioned back in lecture 22 that in a really formal sense, if you want to show that a graph is disconnected, just go find two vertices that aren't reachable from each other. I also gave the advice back in lecture 22 that if you really want to do that, so if you actually want to prove, if somebody really demands that you prove that a graph is disconnected, for this particular graph, the easiest way of doing that is to fixate on vertex J. Because if you show somebody vertex J and say, well, look, this graph has more than one vertex, but vertex J has no neighbors, well, clearly nothing is reachable from vertex J besides itself, and therefore the graph has to be disconnected. In any event, when you have a disconnected graph, you can break it up into connected pieces. So actually vertex J itself would be one of them, and so would this piece here, and so would this piece here, and this piece here, and this piece here. We could even go so far as to view this big graph as the union of 5 smaller connected graphs. And we call those things connected components. Any undirected graph, even a connected one really, can be partitioned into connected components. If the graph itself is connected, then it only has one connected component. And similarly, if it has more than one connected component, it must be disconnected. So I suppose the question is, suppose the graph is not connected, can I isolate, can I identify all of its connected components? And the answer is, well, yes, basically I just run a bunch of traversals instead of only one. So I want to formally define connected components first, and later I'm going to define something analogous to a connected component for directed graphs, and rather unsatisfyingly, the definition I give for that will not look very similar to this at all. For undirected graphs, I will define a connected component to be a non-empty set of vertices, such that for every vertex in the set, all of the vertices reachable from that vertex must also be in the set. So in this case, the set A, B, G, H, and I That would constitute a connected component by this definition. Because if I pick anything in the set, like vertex G, and I look at all the vertices reachable from vertex G, sure enough, all of them are in the component. All of them are in the set that I created. On the other hand, if I, let's say, omit vertex I, so C is now only these 4 vertices here, then the definition does not apply. This would not constitute a connected component, because if I look at all the vertices reachable from vertex G, for example, there is one vertex missing that is not in my set. So a component is a collection of vertices such that if I look at one vertex in the collection, any vertex reachable from that vertex is also in the collection. And notice that if I perform some traversal rooted at any vertex in my component, so suppose I believe this is a BFS rooted at vertex F. It's useful to have that skill of looking at a traversal tree and deciding whether it's a DFS or BFS traversal and trying to figure out its starting point. So it turns out, I guess this is a BFS starting at vertex F. Notice that if I do that BFS, I manage to hit every single vertex in the same component as F. This is something we already know. I've actually used this property a few times already. So I used this a couple of times back in lecture 27, for example. So if I perform a traversal rooted at any vertex, I will visit all vertices in the same component as that vertex, and it seems like this starts me on the way to having a way of identifying all of the connected components of a graph. I just run traversals until all vertices are visited. So here's our task. Given a graph, identify all of the components of the graph. Now, there are lots of ways I could do this. I could choose to view a component as a list of vertices, in which case my goal is to make a set of lists, one list per component. That's one option. That's a bit clunky conceptually. Like, we could do that pretty easily with code, but describing it is a little bit more clunky because, how we represent our lists and so on. So instead, I'm going to just label each component with a number. So let's say this component can be component number 3, and this component can be component number 1, whatever. And then my goal is simply to tag each vertex with its component number. Because if I do that, if I just have each vertex associated with a number corresponding to its component, it's very easy for me, if I want a list of all the vertices in a particular component, to recover that information. So my goal in this case will simply be to compute a table where each vertex is mapped to some numerical index that gives its component number. And my goal, I'll start out with each vertex being given an invalid component number. My goal is to not stop until every vertex has been assigned to some component. Notice, of course, as usual, that because this is a nice diagram, it's pretty obvious which vertices fall into which components. It's very easy for us as humans with our superior pattern matching ability to go through and pretty quickly say, there's one component, there's another one, there's another one, and there's another one. There are 4 components in total. Just be careful about that. That's because of the picture, not because it's an easy problem to solve. All right, so what I could do is basically just go through all vertices, and if I find an unvisited one, I just run a traversal rooted at that vertex. So here I've done a BFS traversal rooted at vertex A, although I could just as easily have done DFS. And then every vertex that I visit from that traversal gets added to component number 1. All right, and then I just keep looking at other vertices in the graph. Next time I find an unvisited one, so I'd probably write an algorithm that goes through in alphabetical order. So the next one I see will probably be vertex C. When I see an unvisited vertex, I run a traversal starting at that vertex, and I label all the vertices that I see with the next available component number. So I guess that would mean these 3 things all get added to component number 2. Okay, so there's component number 2 there. And then I just keep going until all vertices are visited. Okay, so there's component number 2, there's component number 3, and there's component number 4. So we have a traversal pattern here that we've actually seen before. If you think back to that DFS-based topological sorting algorithm at the end of the last lecture, this is basically the same trick I used there. So even though I am technically running a bunch of different DFS or BFS traversals, in a sense, I can think of it as one long traversal that just keeps stopping and starting. So that's what I said at the end of the last lecture, and that terminology has sort of grown on me since then. I've thought a lot about that way of thinking about things, and I sort of like that way of characterizing this. Although it is true I do have a forest of separate traversal trees, in a sense, I did just do one big traversal that had to stop and start. And I never visited any vertex more than once, and it would make no sense for that to happen because I'm working inside of isolated systems. I'm doing traversals of separate pieces of my graph. In any event, because of that, we can assert, just like at the end of the last lecture with topological sorting, that because every vertex gets visited only once, once, I only ever look at each edge twice, once from each endpoint, and so even though the traversal stops and starts, it actually is just basically one long traversal. It has the same running time as a single big traversal over all vertices, which means I'm able to identify all of my connected components again in linear time. I'll take this moment to observe that we have had some amazing luck with linear time recently. Notice that all of the problems that we've tried to solve so far with graphs, we have been able to find some clever trick that has allowed us to solve it in linear time in terms of the number of vertices and edges. The only thing I can think of, in fact, that has been greater than linear in terms of graph stuff so far has been the space complexity of adjacency matrices. That is, any of the algorithms we've used, all of our traversals, even our applications, even things like topological sorting have ended up being linear time. So the question is, how much longer can we keep this streak going? And I'll spoil it and say, surprisingly long. So here is pseudocode for that the algorithm to isolate the connected components. This pseudocode, though, is DFS-based, even though the previous example actually did use BFS trees. Here is some pseudocode, I guess just to be fair, to provide equal time. Here is some pseudocode that uses DFS. And if you compare this to our DFS-based topological sorting algorithm from the last lecture, it looks very similar. So we've got an off-the-shelf recursive DFS. It's got one, I guess, unique feature, which is that as part of visiting each vertex, I do assign that vertex a component number, which gets passed in from outside, and every vertex visited by a particular recursive DFS process gets assigned the same component number. So component numbers are fixed from outside of the actual DFS traversal. And then down here, the algorithm that actually performs the identification of components creates an array with an element for each vertex. And remember that, as with adjacency lists, I am choosing to represent my component tagging as an array. So that is, I've got a bunch of vertices here, and I'm saying, well, let's tag each one with its component number. I'm choosing to think about that in terms of an array with an index for each vertex that I then assign the component number to. But just like with adjacency lists, there's no requirement that I physically use an array for this. That is, when I go to implement this, I could have the component number just be a field in my vertex object, for example. There's lots of ways that are equivalent to having an array with one element per vertex for me to implement this. I just choose to use an array because I have to choose something for my pseudocode. So then I start with component number 1, and then I iterate through every vertex of the graph. If I encounter an unvisited vertex, which would be a vertex which does not have a component number, well then I guess I found a new component. So I run a DFS beginning at that vertex, and I assign every vertex that's visited the component number that's next in the sequence. And then I increment my component number. And for similar reasons, so I'm not actually going to go through the analysis in detail, but for similar reasons to our DFS-based topological sorting algorithm, because we can show that this only visits each vertex once, because I never visit a vertex once it's already been assigned a component number, and the very first thing I do once I visit the vertex is give it a component number. Since every vertex is visited only once, and since all of the other usual constraints of DFS apply, we can show that the total running time of this entire process is linear in the number of vertices and edges. Now, here is the place in the lecture where I provide some non-visually pleasing diagram just to demonstrate that finding components isn't as easy as it looks. So we had, in the last few examples, the luxury of a nice diagram. So a diagram where it's easy for us as humans to glance at it and decide whether the graph is connected, and if not, to find its connected components. That is a luxury that is a product of the diagram. It's the product of somebody making you a nice drawing. It's not something the algorithm has access to. For example, suppose you have to identify the connected components of this graph here. Now, I don't think this is as hopeless as it was back in lecture 22. So we know, for example, how to perform graph traversals. So I could actually do that. I could say, okay, well, let's look at vertex A, and we'll just try running the algorithm that we just came up with. So we found vertex A, it's unvisited, so let's put it in component number 1, and then we'll just perform a traversal starting at vertex A. I guess if we do let's do a DFS here. So I'm going to go over to vertex K. There we go. And then that means vertex K is in component number 1. And then I keep going with my DFS down to vertex J. Okay, vertex J is in component 1, 2. And then I wander over here to vertex D, and then I get stuck. Vertex D is a dead end, so I go back up to vertex J, where I'm also at a dead end. I go to vertex K, also a dead end. I go back up to vertex A. There are more neighbors to visit, so I go down to vertex P. So vertex P is now in component 1, and I go over to vertex L, which is in component 1, and then over here to vertex E, and then vertex Q, and then I get stuck again, and I have to unwind, and I actually eventually realize that I visited everything I possibly could. And so component 1 is now going to be vertex A, vertex K, J, D, E, L, P, and Q. Okay, so without the luxury of a nice diagram, you can see that this problem isn't really trivial. That is, I at least have to do a traversal to figure out what is accessible from what other vertices, and therefore to find my components. So I could run the algorithm on this. There's component number 1. The next one, if I start at B, I get component number 2. Then I get component number 3, and then component number 4. So keep in mind the problem is way easier when you have a nice diagram, in a sense because the person who made the diagram arranged the vertices to solve the problem for you. It was pre-solved. If the graph is a jumble like this, you do sort of have to do work to solve the problem. Okay, so what have we talked about so far? We've talked about the fact that I can use a single traversal to test connectivity in an undirected graph, and if I want to find the components of an undirected graph, I could use a series of traversals, or alternatively, you can think about it as one traversal that just starts and stops. And both of those operations, testing connectivity and finding components, can actually be done miraculously in linear time in the number of vertices and edges. So let's talk about directed graphs. Here is a directed graph. Is it connected? Well, that's a hard question because we don't know what connectivity is, and it's going to become clear pretty quickly that our definitions for connectivity don't make sense on directed graphs as they are written for undirected ones. And the reason for that is, let's consider vertex E and vertex Q. So reachability is not symmetric. We already know that. And notice how I can get from vertex E to vertex Q. I'm going to bravely attempt to come up with a path on the fly here. I think if I go up to vertex H and then down to vertex C, over to vertex K, and then I swoop down through vertex I, sure enough, I can get from vertex E all the way to vertex Q. Great, so Q is reachable from E. And then I glance at this graph, and via my superior human pattern matching skills, I say, hey, this graph looks pretty connected, right? There are no islands of vertices floating around in space, so that means the graph is connected, right? And the answer is, well, not really, because if I look at vertex Q, notice that vertex Q has no outbound neighbors. Well, that's a pretty good sign that nothing is reachable from vertex Q. So I can get from vertex E to vertex Q, but I have no way to get back. I can't get from vertex Q to anywhere. So it doesn't make sense to call this graph connected because if we define connectivity in terms of reachability, it doesn't really meet the bar. It's not connected in that sense. So what do? Okay, so the logic I've used so far in this course with directed graphs is if you have edge directions, you damn well better respect them. That is, why do you add directions to your edges if you are going to ignore them? The reason I say that is there is some instinct to look at this, as I said, and say, hey, it looks connected. By an undirected standard, it's connected. So can't we call it connected? I don't think that that's going to fly. We could try that, but we shouldn't call that connected. If ignoring the edge directions results in me thinking the graph is connected, really I don't have full connectivity. I've got some watered down, diluted, those aren't the right words, maybe we'll say weak version of connectivity. So I guess we can define that, I guess, for the sake of mending fences. So a directed graph is called weakly connected if, when you convert it to an undirected graph, and the way we do that is by just ignoring all the directions on edges, and in cases like this, so notice that these two edges here, if I ignore edge directions, I end up in a bit of trouble because if I ignore edge directions, there appear to be two edges between vertex P and vertex D. That is not allowed. You're not allowed to have two edges between the same pair of vertices in an undirected graph. What we do in this case to collapse this thing down to an undirected graph is if we have parallel edges, we just pretend there's only one of them. So we do something like this. So a directed graph is called weakly connected if when I collapse it down to an undirected graph, I get a connected graph. Okay, so that's weak connectivity. And I think it's important that we call it weak connectivity because I'm not actually using any properties of the directions of edges at this point. I'm pretending I didn't have a directed graph. And that doesn't make any sense because if I have edge directions to begin with, they must mean something to me. There must have been a reason I defined my graph to be directed. So we're going to find in this course that rarely do we actually use weak connectivity for anything. We do refer to it occasionally because it's a good point of reference. That is, it's certainly true that if a directed graph does have islands of vertices floating around, it isn't even weakly connected, and that can help us in certain cases. So although weak connectivity plays into some things that we reason about, it doesn't tend to be that useful in the grand scheme of things, because if we have a directed graph, the directions probably mean something. So if I look at the graph that I started with here, because if I collapse it down to an undirected graph, I get something connected, we can say that this is a weakly connected graph. What we want, though, is a definition of connectivity that somehow leverages the directions of edges. What we want is something that isn't weak connectivity, we want strong connectivity. And I can define that. And what's really weird about this definition is it is the same definition that I would use in the undirected case, only I use the word reachable to refer to directed reachability, the stronger form of reachability that applies to directed graphs. So a directed graph G is said to be strongly connected if, when I choose any pair of vertices U and W, it is the case that W is reachable from U. And that's the same definition that we had way back in our definition of undirected connectivity. So let's try that out on this graph. If I pick vertex E and vertex Q, it is true that Q is reachable from E. But on the other hand, if I pick the pair E, Q, well, Q is reachable from E. Good so far. Now, what if I pick instead the pair Q, E? Well, it is not the case that E is reachable from Q. Okay, well, that means that this graph is not strongly connected. Since there is no path from vertex Q to vertex E, or frankly from vertex Q to anything besides vertex Q itself, this graph is not strongly connected. Okay, so what does a strongly connected graph look like then? Okay, well, how about this one? Here is a strongly connected graph, and we'll try that out. Let's pick two vertices, vertex D and vertex C. Okay, so can I get from vertex D to vertex C? The answer is yes. So I just wandered to vertex H, and then up to vertex E, and then down to vertex G, and over to vertex C. Okay, great. What about if I want to get from vertex C to vertex D? Okay, then I walk down to vertex E, I walk down to vertex H, I have to take a bit of a detour here. I go over to vertex F, I go up to vertex A, and then I go across here to vertex B, and then finally down to vertex D. Okay, so it was a bit of an exhausting path, but I did make it. So I can get between vertex D and vertex C, and between vertex C and vertex D. And it turns out, you can try this yourself, that if I try any two vertices, there will be a path from one vertex to the other and a path back. Of course, the paths aren't going to be the same necessarily. That wouldn't make very much sense. But in this graph, every vertex is reachable from every other vertex. So our first task is design an algorithm to test whether a directed graph G is strongly connected. Okay, so the definition I think that's the most tangible here to work with would be to say the graph is strongly connected if, no matter where my starting point is, every vertex is reachable from every other vertex. In other words, if I do a traversal starting at vertex A, I should be able to reach every other vertex. And if I do a traversal starting at vertex B, I should be able to reach every other vertex. If that holds for every vertex in the graph, well, then it must be the case that there is a path from every vertex to every vertex, and therefore the graph is strongly connected. Now that sounds like a decent amount of work, but I do have an idea. I mean, that is an algorithm that should work. I'll just do a traversal rooted at every single vertex in my graph. And then if every traversal reaches every vertex, well then my graph is strongly connected. So that's my first try. Perform a traversal rooted at each vertex. Okay, so there's a traversal rooted at vertex A. It reaches everything. There's a traversal rooted at vertex B. It also reaches everything. And just hold up a minute. Notice that these two traversals are really, really similar. Now that's fine, fair enough, luck of the draw, but what I want to observe, a sort of thing I want to put in our pocket for later, is that it does appear as if there's a lot of duplicated work here. It looks like when I did the traversal for A, and then I reset everything and did a traversal for B, I ended up actually visiting a lot of the same edges that I was visiting before. Not all of the same. The traversal tree could be quite different, but in this case, there was quite a bit of redundancy, and I might want to put that aside for later, just in case the algorithm I come up with ends up being a little bit it's slow. All right, there's a traversal rooted at vertex C. Again, a decent amount of duplication. There's one at vertex D, there's vertex E, there's vertex F, there's vertex G, there's vertex H. Every single one of these traversals did reach every vertex, and therefore I can assert that the graph is strongly connected. Okay, so I guess before we talk about the running time, there's also a question of what about a graph that isn't strongly connected? So this is the graph from earlier, and we know this graph isn't strongly connected. But notice that if I do a traversal rooted at vertex A, it does actually reach everything. And that's just because vertex A is just in a good position, I guess. So unlike vertex Q, which can reach nothing, vertex A has this unique property, just what a coincidence, that it's able to reach every other vertex. However, if I keep doing other traversals, because we know this graph is not strongly connected, at least one of those traversals will not be able to reach everything. I've got my money on Q, definitely. If I do a traversal rooted at Q, I can't expect it to reach just about anything. It turns out, though, that I don't have to go that far. If I go to vertex B and perform a traversal, notice that it does not reach a lot of other vertices. So there is no path from vertex B to vertex C, for example. And that means that this graph is not strongly connected. I can give up as soon as I discover any vertex from which a traversal does not reach everything. Now, on the subject of redundancy, I do want to observe that there is a bit of redundancy between these two trees as well, these two traversal trees. We're going to talk later about the redundancy that exists in traversal trees. What I will observe about this traversal tree here is that this is a BFS tree. And one way that I know that is notice how many neighbors A has, basically. Notice that A has so many children in this tree. That's sort of a sign it's a BFS tree. It's not guaranteed. You can design graphs where a DFS tree looks sort of like this, but that's a hint that we're probably doing BFS. It actually turns out if I do DFS, there is even more redundancy between these two traversal trees. And that turns out to be a big deal later. Okay, so in the worst case, that is, you could argue that in this situation, I can give up on my strong connectivity test very early. As soon as I perform the traversal at vertex B and I observe that I never reach, for example, vertex C, I can say, okay, then the graph is not connected and we're done. But in the worst case, which I guess is the case where the graph is connected, I have to perform this number of traversals. Now, actually, for the sake of discussing this out loud, I'm going to use n and m. So the number of vertices is equal to n, and the number of edges is equal to m. The notation here is looking pretty nasty, frankly. So since I need to do n traversals in the worst case for testing strong connectivity, the running time is going to be, well, okay, the running time of one traversal is n plus m asymptotically. So if I'm doing n traversals, I'm doing this amount of work, big theta of n times n plus m, which is equal to big theta of n squared plus nm, which is a bit of an unsavory running time, frankly. There's a lot I have to do there, and I'll show in a minute that we can boil that down a little bit. So the worst case running time is n squared plus n times m. And before I say anything else, I want to clarify that there is something we can do to simplify this, which is to observe that if the graph is weakly connected, or actually, if the graph isn't weakly connected, it clearly isn't strongly connected. So if we consider the case where our graph is weakly connected, there's a neat observation I can make. This is an observation about undirected graphs. If I know that my graph happens to be weakly connected, that means that there have to be at least this number of edges, that is n minus 1 edges. This is a property that we proved back in lecture 23. Basically, it's that if you have a graph with fewer than n minus 1 edges, the graph is never going to be connected in the undirected sense, which means it won't be weakly connected in the directed sense. So what's clever about this is if I want to think about the running time, if I want to, derive some meaning from this expression, what I could do is observe that if the graph has even a hope of being strongly connected, it must be weakly connected. And therefore, if I assume the graph is weakly connected, that means that the number of edges has to be at least equal to n minus 1. And I can use that, and I could take this running time here, which, as we saw before, is n squared plus nm, and I can observe that if m is at least equal to n minus 1, then this whole thing is, I'm actually going to say asymptotically. This whole thing is asymptotically just going to be n times m. That is, n can be bigger than n, but it can't really be that much smaller. And so the n squared sort of falls by the wayside there, because m is going to be at least equal to n minus 1, which is big, so n times m will be big theta of n squared. So I could therefore basically just treat this running running time as big theta of number of vertices times number of edges, so n times m, rather than worrying about that n squared in there. Now the issue with that is that we know that in the worst case, the number of edges, it could actually be n squared. And that means that this strong connectivity test on a very dense graph, a graph that coincidentally happens to be, well, maybe not that coincidentally, dense graphs might be more likely to be strongly connected and therefore more likely to require more traversals before the strong connectivity test can end. And on dense graphs with lots of edges, the running time could end up being n cubed. It could end up being the number of vertices cubed. Now, as usual, I have to give a disclaimer here that there's nothing wrong with n squared, and in fact, there's nothing wrong with n cubed. We're only a few lectures away from seeing some algorithms where getting an n cubed running time is pretty good because we're doing a lot of really important and difficult work with our algorithm. However, because we've had such a good run with finding linear time algorithms so far, I do have some motivation to try to at least get this n cubed out of there. Maybe I can settle for an n squared algorithm, but it does feel like I can probably do better than n cubed at least. In this case. Now, we're actually going to have much better luck than that. It turns out that the next observation we can make is going to bring down the time of our strong connectivity test dramatically. So the question is, can we do better? I guess I got ahead of myself there. The answer is yes, we can do better. Okay, so let's think about what we need to do to test strong connectivity. What I want to assert is that it's possible to reach any vertex from any other vertex. Fundamentally, I can define connectivity in terms of reachability. So a graph is strongly connected if, when I pick any two vertices, it is the case that one vertex is reachable from the other. And that implies, of course, that the relationship also works in reverse because I could have chosen the vertices in the opposite order. So it's all based on reachability. Okay, so is it necessary that I find, to show that D is reachable from E, is it necessary that I explicitly find a path from E to D? Well, that certainly would prove that I have reachability, but it's not necessary. To assert that a graph is strongly connected, all I have to do is to assert that any pair of vertices is reachable from each other. And to assert reachability, I don't actually have to find a path. I just have to assert that a path does exist. And if I think about that, what that's really telling me is that if I can just reason about reachability, I might be able to get a strong connectivity test, I don't know, that's a bit less literal than a test that does a traversal rooted at each vertex. So how about this? Suppose I do a traversal rooted at vertex A, and I'm able to verify that every vertex is reachable from vertex A. Suppose that separately, I am able to show that vertex A is reachable from every vertex. I claim that that is sufficient for the graph to be strongly connected. And here's why. Suppose that I know that every vertex can reach vertex A. In other words, I can get from, let's say, vertex C to vertex A. Suppose also that from vertex A, I can get to any other vertex, like vertex G. Well, then if I want to get from vertex C to vertex G, all I have to do is use vertex A basically as a hub. I walk from vertex C over to vertex A, and then I walk from vertex A back down to my ultimate destination, vertex G. So in fact, I could compact my entire strong connectivity test into testing a certain property of vertex A. Can I get from vertex A to everything else? And can I get from everything else back to vertex A? If both of those statements are true, then the graph must be strongly connected. And what's nice about this is that since I'm reasoning about reachability, I don't have to get too tied up in the notion of paths, because it is true. Notice how here I can actually get from vertex C to vertex G without going all the way to vertex A. There is a much more direct route via vertex E. And in fact, if I were to call the thing I did there a path, I would actually be wrong because I repeat vertex E. And so if I restrict myself to our path-based view of reachability, then I end up, although this property is still true, I end up with a real mess on my hands as far as proving it is concerned, or justifying it with my strong connectivity testing. If instead I just reason about reachability, it doesn't make any difference that when I want to reach vertex A from vertex C, and then go from vertex A back to vertex G, that I repeat something, because I have shown there is a way of wandering through my graph such that I start at vertex C and end up at vertex G. And it's somebody else's problem to find the most direct route. All I have to assert for strong connectivity is that reachability holds. Okay, so there's an idea for a strong connectivity test. Test whether I can start at A and reach everything. Okay, that part's easy. I just run a traversal rooted at A. But how can I check whether every vertex can reach A, whether I can get from every vertex back to A? And it turns out this is actually an application of the transpose graph. What I want to do is, given a graph in some vertex, find the set of vertices that, you give me some vertex V. I want to find the set of vertices U such that V is reachable from U. That's a really weird way of phrasing this, and it's not helped by the fact that the way we talk about reachability in English is this weird backwards phrase. What I'm really asking is, I want a traversal of inbound reachability. We can think of the reachability I was working with earlier, where I do a traversal from A, as outbound reachability. So if I do a traversal starting from vertex A, I might get something looks sort of like this. Here's the beginnings of a traversal. What this is telling me is I can start at vertex A and I can reach in an outbound sense. I can get to vertex B or vertex D or vertex E. What I want to test, in fact, is whether I can get from a vertex to vertex A. In a sense, I want to do a traversal backwards along edges. Now, of course, I'm allowed to do that. I'm always allowed to walk backwards along an edge if I have a good reason. And what I want to do here is a traversal that looks sort of like this. This traversal, which walks backwards, is telling me that I can get from vertex D and from vertex H and from vertex F to vertex A. I'm doing a traversal of inbound reachability. So I've spoiled a way of doing that. I could just do a graph traversal where I walk backwards along edges. That is, instead of visiting outbound neighbors, I visit inbound neighbors. And although that is valid, and it's valid to think about our traversal being modeled that way, it still feels a bit weird because we fixate all this time we have been fixating on following edges in the right direction. So in a sense, we can think of this as a cop-out, but because I want to employ my off-the-shelf traversal algorithms like DFS and BFS, which always walk forwards along edges, what I'm going to do is not perform a traversal that walks in reverse, although maybe when I go to implement the code, I might actually write it that way. To talk about this, to reason about it, I'm going to think about the transpose graph. So recall that the transpose graph, here's some graph G, some directed graph G. The transpose graph of G, which I denote by G transpose, is the graph produced by flipping the direction of all edges. So notice how in my original graph there's an edge from A to B, and in my transpose graph there is an edge from B to A. I thought a bit before recording this, if I'm going to call this the transpose graph, what do I call the original graph? And I realize I just keep saying original graph, so I suppose that's the term we're going to use. G is the original graph, G transpose is the transpose graph. Okay, so let's take a look at paths between a graph and its transpose. Notice that if I go to the transpose graph and I find a path, let's say this path from A to G, notice that this is a forward path in the transpose graph, but it's a backward path in the original graph. So if I find an AG path in the transpose graph, that's actually equivalent to a GA path in my original graph, which isn't too surprising. I flip the direction of all edges, and so the orientation of all paths also gets flipped. Now, what's significant about this means if I go to my transpose graph and I do an ordinary traversal, so I don't modify my traversal logic at all I'm doing is changing which kind of graph I'm using. If I do an ordinary traversal in my transpose graph, the traversal tree that I produce, so if we take this, what I've actually done here is the traversal tree on the right, this thing over here, is a BFS of G transpose rooted at vertex H. What I've done over on the left is I've just taken the same edges and I've overlaid them on the left. So I'm not doing a traversal in G, I'm just taking my traversal tree from G transpose and visualizing it on top of G over on the left. So the observation I'm making here is if I do a traversal rooted at vertex, let's say vertex H in G transpose, that's going to visit all of the vertices U such that H is reachable from vertex U in G. In other words, here, for example, there's vertex D. Notice how what I have in my traversal tree, once I map it back over to G, is a path from D to H, as opposed to what I'm used to, which is an outbound path. This is a big deal because what it's telling me is that my new strong connectivity test, leveraging this observation, can actually be done with just two traversals. All I have to do is do an outbound traversal, that would be to create the blue path, and then do an inbound traversal, or we could view that as a outbound traversal in G transpose to produce the red path, the inbound path. Okay, So my algorithm idea now is to test if a graph is strongly connected, just choose some vertex v, so we could have chosen vertex h there, and perform two traversals. One traversal rooted at vertex at my chosen vertex in G, and one traversal rooted at my chosen vertex in G transpose. If both traversals reach all vertices, well, that means that G is strongly connected. Because suppose I choose H as my hub vertex here. If I discover that all vertices can reach vertex H, and that H can reach all vertices, well, then all vertices can reach each other. And that's a consequence of transitivity of reachability. Okay, so let's use, I guess we've chosen to use vertex A as my hub vertex after all. So notice that here, if I do a traversal rooted at vertex A, every vertex is reachable from vertex A. The problem is, if I do a traversal rooted at vertex A in G transpose, it exposes the fact that there actually are some vertices that cannot reach vertex A in my original graph. So notice how a traversal rooted at vertex A over here will never get to vertex F in G transpose because vertex F doesn't have any inbound neighbors. That is, if we flip everything back over to our original graph G, what we're really saying is F actually has no outbound neighbors. So while it's possible to get from A to F in my original graph G, there is no way to get from vertex F back to vertex A. And this is one way of showing that this graph is not strongly connected because there are some vertices that cannot reach vertex A and therefore may not be able to reach other vertices as well. So I was able to do this strong connectivity test with only two traversals. And this is great because one traversal takes linear time and two traversals, two being a constant, also takes linear time. That's a big deal. I've gone from v times e time, which could be as much as number of vertices cubed, right back down to linear time. And so our winning streak continues. We've found already in this course, there are plenty of topological sorting and things, plenty of algorithms that seem like they're going to get us more than linear time, and we find some clever trick that brings us back down to linear time. And that winning streak is continuing. The question is, can it sustain itself through the rest of this lecture? So let's think about directed graphs that are not strongly connected. So we have this idea of a connected component, although it's a little bit more complicated in a directed graph than an undirected one. As you can see here, we call these things strongly connected components. And I've highlighted them here. So there's one, there's another. Notice how the components do actually have edges running between them. So it's true that if I look inside of one of these components, let's take a look at this component here. If I look at any vertex in the component, I can reach every other vertex in the component from my starting point. So if I pick any pair of vertices in one of these strongly connected components, those vertices will always be reachable from each other. And the same is true, let's say, G and P or R and D or whatever, any two vertices in the same component. But notice how there actually are edges between components. Now, I'll come back to this at the end of the lecture. What I want to observe is first, that is allowed, absolutely. But notice how if I look at, we'll call this thing component A and this thing component B. There are edges from component A into component B. And actually, there are also edges from other components into component A. That's fine. But there are never going to be edges both from component A to component B and back. Because if there were, that would mean I have one big component after all. So in other words, it's possible to reach vertex D from vertex H. But it is not possible to get from vertex D to vertex H. Because if it were, I would just have one big component. So the relationships between components do sort of, create a hierarchy of sorts. And we'll see that hierarchy formally in the last couple of slides of this lecture. The key thing to observe is clearly strongly connected components are a bit more complicated than regular connected components in undirected graphs because there can still be edges between those components versus in the undirected case where there can't. A formal definition, and I warned you earlier that my formal definition of strongly connected components doesn't look very much like my definition of undirected connected components. A strongly connected component is a maximal, oh that's a nice word, a maximal set of vertices C such that the subgraph induced by C is strongly connected. Okay, that's a bit of a dense definition, so let's work backwards. Here is a component here. So we'll just give it a name. We'll call it C. And C consists of the vertices D, G, P, and R. Now, notice that if I take my collection of vertices C and I create the induced subgraph induced by the vertices in C. So recall that when I create an induced subgraph, what I'm doing is taking a collection of vertices and I'm bringing in all of the edges between those vertices from my original graph. So any edge that does not connect two vertices from my collection and any vertex not in the collection gets discarded. Okay, so I look at my induced subgraph. Notice that this induced subgraph here is strongly connected. Any two vertices in my induced subgraph are reachable from each other. Okay, so a strongly connected component is a set of vertices such that if I take the induced subgraph, that is a strongly connected graph. Okay, but what about the word maximal? Okay, so the word maximal there is to keep me from taking too few vertices. So suppose I did something like this. Suppose I delete vertex D. Okay, so now my induced subgraph, I'm sorry for the mess here, my induced subgraph is just these three vertices here. Notice that if I look at two vertices in this collection of three, they are always reachable from each other. I can get from R to G and from G to P and from P to R, whatever. But this is not a strongly connected component because something is missing. So by forcing my set C to be maximal, and the word maximal in this context means that the set cannot get any bigger. If I force C to be maximal, that means it only counts as a strongly connected component if all of the vertices in the component are in the set, basically. It doesn't allow me to take some subset of the component. So the set C is maximal if no other vertices can be added to C such that the subgraph remains strongly connected. And we can try that out. Suppose that this is my collection C as before. Notice that if I try adding even one other vertex, the result, if I induce the subgraph, is not strongly connected. Okay, so we know what strongly connected components are. The task here is to design an algorithm to identify the strongly connected components of the directed graph. This is going to be a challenge. So we are at slide 62. I believe that the last slide of the lecture is slide 137. So just about half of this lecture is going to be spent on this problem. Design an algorithm to go and find the strongly connected components of a directed graph. Now, we actually already have a pretty good first try ready, which is that we can use our strong connectivity test over and over again. So we can do the same trick we tried back with undirected graphs. So what I could do is I could say, let's pick a starting point like vertex A, and then find all the vertices reachable from A. And it turns out in this graph, I'll spoil it, it's actually everything. We already saw with the same graph, if I do a traversal rooted at vertex A, it does reach every single vertex. It also turns out, and this is pretty clear visually, that very few vertices can reach vertex A. The only vertex that can actually get back to vertex A is vertex F. So what I could do is two traversals, I could do my strong connectivity test, and any sets of vertices that are in both traversals, that would form one component. And so I'll show that off visually here. So I choose some arbitrary vertex like vertex A, and I do both traversals. First, I perform a traversal rooted at A in my original graph, G. In this example, notice that if I perform a DFS traversal rooted at vertex A, I actually am wondering whether this might be a typo. Let me just think about this. Yeah, it turns out, sorry, this is actually a BFS traversal. So I was worried this was coming, but yeah, there's a typo here. And as before, we can observe this is clearly going to be a BFS traversal because if A went down to vertex B in DFS, it would go to vertex, oh no, wait, this is a DFS. So sorry about that, I got ahead of myself. I didn't have enough confidence in my own slides. This does look like it is indeed a DFS traversal after all. So because it's a directed graph, I shouldn't impute the behavior of DFS in the undirected sense. So this number of children in this case actually does make sense because we are working with a directed graph, and so the fact that A has lots of children in the traversal tree doesn't mean I'm doing BFS. It could just mean that vertex C is otherwise not reachable. So I probably went down here to go to vertex B, I came back up, went to vertex C, I couldn't get from vertex C to vertex H, so I ended up visiting vertex H later. Okay, so sorry about the fumbling there. It does look as if this is the one example of a case where I do not have a typo in the slides. So I start at vertex A, I do a traversal, and I reach everything, as it turns out. We saw on the previous slide, though, that the component containing A does not contain everything, far from it. So I do a traversal in G, rooted at vertex A, and I'm going to, for the sake of this example, I'm going to adopt a standard shading policy where when I do a traversal in the original graph, the vertices that are reached only by that traversal will be shaded in blue. Okay, so every vertex was reached if I started at vertex A in the original graph. Okay, so now what I do is I go into my transpose graph and I do a traversal starting at vertex A there. Notice that the only vertex that gets hit by that is vertex F. So vertex F was also visited by my traversal in the original graph, and therefore I'll color it orange. It was visited by both traversals. And so vertices that are visited by both traversals with a given starting point are shaded in orange. And the starting point itself is considered to have been visited by both traversals, of course, as well. Okay, so the set of vertices that were visited by both traversals is then going to be a strongly connected component. There it is. I now have one strongly connected component. And now if I want to find the next one, I just go find some other vertex that has not already been added to a component, and I repeat the process there. Okay, so now I go to vertex B, and I run a traversal rooted at vertex B. There it is. Then I run a traversal rooted at vertex B in the transpose graph. And we observe that, okay, so if I start at vertex B in the transpose graph, I go up to vertex A, I go down to vertex F. I'm going to shade vertices in red if they are visited by the traversal of the transpose, but not the traversal of the forward graph. So we can see here the blue vertices are vertices that were visited by my traversal of G. The red vertices are vertices that were visited only by my traversal of G transpose. And in fact, there are no vertices that were visited by both traversals. And therefore, B ends up getting added to a component by itself. That's it. And I'll back up 2 slides to show a slide that I skipped, which is that there is an optimization I could do here, which is that it won't change anything asymptotically, so I'm not going to bother with it in the example. But if I actually wrote the code for this, which is that I already put A and F into a component, and so I could mark them as permanently off limits and just never bother visiting them again. They're never going to be added to another component, but I could mark them as off limits so I don't waste time traversing them, as you'll see I have done here. So I actually am traversing A and F, even though they've already been consumed by some component. So if I do that, if I mark them as off limits, it turns out asymptotically nothing changes, but it might be a good way of speeding some stuff up in practice. Okay, so vertex B ends up getting added to a component all by itself. And similarly, if I do the same process at vertex C, so if I do a traversal rooted at vertex C in G, I visit all the blue vertices. And if I do a traversal rooted at vertex C in G transpose, I visit all the red vertices. And there's no overlap, so vertex C ends up in a component by itself. But don't worry, we'll get to an interesting case pretty quick here. Okay, so if I do a traversal rooted at vertex D in my original graph G, it turns out the only vertices visited by that traversal are these ones. And if I do a traversal rooted at vertex D in G transpose, I actually visit everything. So all the red vertices, or everything except for Q somehow. The red vertices are vertices visited by my traversal in G transpose only. And vertex Q is actually inaccessible in G transpose because in G transpose, Q has has no inbound neighbors. It has inbound neighbors in G, but not in G transpose. So the only vertices that were in both traversals, that were visited both by a forwards traversal in G and a traversal in G transpose, are the ones in orange and D itself. So those get wrapped up into my next component. Okay, similarly, if I do a traversal in E, starting at vertex E in my original graph G, I reach all of the blue vertices. If I do a traversal rooted at E in G transpose, I reach all of the orange vertices and all of the red ones. The only vertices that were reached by both traversals are these ones, and so this becomes a component. Okay, and then finally, I identify these 2 things, and then Q gets to be a component by itself. All right, so I was able to identify all of the strongly connected components, although it was quite a bit of work. I had to perform a pair of traversals for a whole bunch of different starting points. Now, the number of starting points, or the total number of traversals, I guess, would be 2 times the total number of components, because each pair of traversals yields 1 component. So a question we should ask is, what does a worst-case input look like? And in fact, the exercise I'll leave to you is to construct one. Construct a weakly connected graph, so a graph that from a distance looks like it might be strongly connected, on which we get the worst-case running time I'm about to describe. Okay, so what is the worst-case running time? Well, it's similar to our initial strong connectivity test. We might have to run a traversal at every single vertex. And since so there could be n traversals, each one taking n plus m time, which gives us again n squared plus n times m. And that could be as bad as n cubed in the worst case, because m could be as much as n squared asymptotically. So that means that our algorithm to find strongly connected components has this, again, rather unsavory running time, given that we've been living in this fantasy world where everything is linear for the last few lectures. So the question is going to be, can we do better? So is there something we can do to reduce this to at least better than n cubed? Maybe we can settle for n squared. If all goes well, maybe we can do even better than that. But hopefully we can do better than n cubed. Okay, so the observation that I made along the way there was that there is significant redundancy in this process. And after all the initial fumbling about whether I was doing DFS or BFS, I am relieved that they were indeed DFS trees, because it turns out the algorithm we are about to meet requires the use of DFS. So it took a while to get here, so we saw this a bit in the last lecture, but we are now seeing some of the key strengths of DFS, and we're going to see them in a big way in the coming algorithm. So the observation I made with that sequence of DFS traversals is there was a lot of redundancy because, for example, when I start at vertex A in my original graph G, I visit everything. So I traverse every vertex. And then later on, when I start at vertex B, I traverse a lot of the same vertices. And in fact, it goes beyond that. Not just that I traverse the same vertices, but I actually generate the same tree. So because we use DFS instead of BFS, and you saw me verify in real time that we did indeed use DFS on the slides, notice that the subtree rooted at vertex B is actually it's the entire, or if I look at the DFS tree at vertex A and then examine the subtree of that rooted at vertex B, what I get is actually the entire DFS tree for vertex B. In other words, when I go back later and I generate the DFS tree for vertex B, I am duplicating the exact same thing I had a minute ago as a subtree of the DFS tree of vertex A. That seems like redundancy we might be able to eliminate. What that sort of tells me is the exact starting point for DFS might, if I choose that starting point well, if I choose it to be a vertex that's able to visit everything else, for example, maybe I can save some work later by keeping in mind some of those results that I saw in that DFS tree when I work with some other vertex, some vertex that's sort of downstream from my starting point. And then something else shows up, and this is actually really weird. This is a property that I didn't really truly appreciate well until I made these slides. That is, the algorithm we're building up to I've had to deal with for years, and it's a bit of an acquired taste, and I don't know if I fully acquired that taste yet, to be honest. But I had not noticed this property fully. I hadn't really understood it until I was making these slides, and until I began. That's why I added the slide to the sequence, frankly. Let's take a look at the DFS tree rooted at vertex A. And now I have overlaid the finished components on top of that DFS tree. So vertex A is just some arbitrary vertex as far as we're concerned. But it happens to have this neat property where I do reach every other vertex from vertex A. There could be several vertices in a graph that reach lots of the other vertices, so this may not be a unique case. I don't have to actually reach all of them to get this thing I'm about to observe. But there's a pattern that shows up if I look at one of these DFS trees that visits everything, and I look at it overlaid on top of the real components. So notice that the DFS tree from A eventually finds its way into other components. Now this is irrelevant to vertex A, but notice that once it gets into a component, it stays there. Notice that if I go inside of this component, the DFS tree stays inside the component. All of the paths that are internal to the component, so between, let's say, vertex H and vertex J, the path in this DFS tree from vertex H to vertex J stays entirely inside of that component. It doesn't leave and come back. Now, if the DFS tree enters a component, it might eventually leave, but all of the paths inside of the component, between vertices in the component, are able to stay inside of the component. So if I go from vertex D to vertex G, notice how inside the DFS tree, the path stays entirely inside of the component. This is actually a property that we can prove. And that's what's so weird about this to me, is that it's one thing for a DFS tree to have a bizarre coincidence like this. It actually turns out that this is a requirement of the way that DFS works. And so similarly, look at how the path between vertex I and vertex K stays entirely inside the component, although that's because K and I are connected by one edge. So this is a property I'm going to prove in a minute on our way to the algorithm that I want to talk about next. And it is the Kosaraju-Sharir algorithm. And this is it. This is the moment. We are now graduating from introductory graph algorithms to intermediate graph algorithms. Now, one of the reasons you could claim this is an intermediate graph algorithm is that we're going to find that the proof of correctness is a huge pain in the neck. And that might be a good reason to say this is clearly a step up from, let's say, DFS or BFS. Okay, that's one reason. I'll take that. But to me, the reason I know that we're now working with an intermediate graph algorithm is that it's named after people. So unlike what we were doing before, which is that we design algorithms and we have to write proofs of correctness and figure out their running time and then prove the running time, well, we have to do all of that for this algorithm. But we also have to deal with academic politics. So in this course, we have, I think, only seen one algorithm so far that was named after people, and it was the BFPRT pivoting scheme for quick select and quick sort, way back in, I guess that was lecture 11. And I mentioned in lecture 11 that when you name things after people, that can be a whole hornet's nest to get into, but that fortunately for BFPRT, it was relatively straightforward since all 5 of the authors published one paper together. That is, this is just the initials of the 5 authors of a single publication. So it's not too controversial to say that the algorithm should be named after those 5 people. In practice, we find, with most of the algorithms that we're going to study, that they were actually invented by multiple people somehow. For example, 2 different people discovered it independently, or one person discovered half of it and somebody else discovered the other half, and so then there becomes this question of who do we name it after? And I will take this time, since we're on this slide anyway, to talk a bit about naming things after people. Some of this is maybe my opinion, but I think this does map on pretty well to the way that the community works with naming things. And it works like this. The reason that we name stuff after people isn't inherently intended to be some honor for the person. That is, it certainly is an honor to have an algorithm named after you. And if you discovered an algorithm, it can be very rewarding to have your name used in conjunction with your algorithm. And so it is an honor, but that's not the reason that we name algorithms after people. The reason we name algorithms after people is that algorithms need names. That's it. And sometimes when an author produces a new algorithm, they give it a name. So for example, once upon a time, somebody wrote a sorting algorithm, published a paper about it, and said, I have named my algorithm Quicksort. And now we call it Quicksort. Even though, as I've observed, of course, by our standards, with worst case running time, Quicksort is not quick at all. And so if the author gives it a name and the name catches on, well, then that's what we call the algorithm. Alternatively, there are some things, there are some algorithms and some data structures where there is a natural name because of some unique characteristic of the algorithm. And so merge sort might be an example of that. Merge sort is called merge sort because its characteristic operation is merging. Same thing with insertion sort or selection sort. Or an algorithm like DFS, depth first search. DFS is a good name because it's descriptive. It actually describes what the algorithm does. There was an inventor of DFS. I actually don't know who it was off the top of my head, but it wasn't necessary to name the algorithm after that person or people because the algorithm has this nice name that's sort of descriptive. And think also of things like red-black tree. Well, ultimately, what a red-black tree does has nothing to do with the colors red or black, but the coloring of the nodes of the tree is a characteristic enough aspect of the tree that calling it a red-black tree is a pretty good way of referring to it in companies that understand what you're talking about. They know what you mean when you say red-black tree. But there are lots of algorithms and data structures out there, and not all of them have some unique characteristic that's obvious on the surface. So we have to name algorithms something. Well, it makes sense if you read about an algorithm in somebody's paper that they published, you might say it's so-and-so's algorithm. You might name it after the person that, in your eyes, discovered it or brought it to your attention. And here's where things get dicey. So the Kosaraju-Sharir algorithm was invented independently by 2 different people. That is, this is not a case where 2 people wrote a paper together. In fact, the paper that we should talk about here is this paper by Sharir. So Sharir published this paper in 1981. The slides are being a little bit, this is maybe a little bit sloppy to say that Sharir discovered the algorithm in 1981. I didn't have a chance. I had to read this paper as part of creating these slides, but I don't recall whether, in many cases with publications, it will tell you in the paper when the journal editors received the paper from the author. In some cases, especially a long time ago. So in 2025, if you were to submit a paper for publication today, and today is May 6th, 2025, if you were to submit the paper today, depending on where you're publishing it, it could be published in a few months, it could be published in a couple of years, and the publication date is the date that gets attached to the paper. So the algorithm I'm going to describe in the next few slides was discovered by Kosaraju in 1978, and a paper was published about it in 1981 by Sharir, but Sharir may have invented it earlier than that. It appears as if these two people discovered this independently, and Sharir would have had no knowledge of Kosaraju's discovery because Kosaraju didn't publish a paper. That is, it's not like they kept it a complete secret. They might have shared details of it with colleagues or written it down themselves personally or something, or sent, I guess they had email back then, sent an email about it, but it wasn't formally published. So logically, it makes some sense that Sharir, who is somewhere else, in a different part of the world, who was thinking about this problem, might have discovered the same algorithm completely independently just by some coincidence. And this actually happens a lot more often than people think. We're going to have quite a few cases in this course where we talk about algorithms that are named after multiple people because several people seem to have independently discovered the same thing. Now, from my end, the way I view this is as follows. In general, if there are multiple discoverers and one of them seriously predates the others, so if Kosaraju discovered the algorithm in 1928 and didn't keep it a complete secret, then maybe we should have just called it Kosaraju's algorithm, because Sharir discovering the same thing 50 years later, that does seem like a little bit too long. However, if two different authors discover the same algorithm in about the same time frame, so within a couple of years of each other, and especially in cases like this where each author deserves credit for one aspect and the other doesn't. So Kosaraju might deserve credit as the first discoverer, but Sharir deserves credit as the first person to write up a paper about it and publish it. And being able to communicate ideas is part of being credited as the discoverer of those ideas. Like, just having an idea isn't enough to claim discovery. You have to have some way of communicating it. So from my end, that is a good argument to name it after both of them. So I'm going to choose to call this thing the Kosaraju-Sharir algorithm. If you look this up in other sources, you will find some sources that call this Kosaraju's algorithm on the grounds that Kosaraju discovered it first. You will find some sources that call it Sharir's algorithm on the grounds that Sharir is the first person to write it up and publish it, and therefore they should get the credit. I think that that's splitting hairs. I think it does make sense to give them both credit. So I'm going to call it the Kosaraju-Sharir algorithm. Now, before I talk about the algorithm itself, I want to prove a couple of other theorems. And it turns out, so theorem A is going to factor directly into our discussion of the algorithm. Theorem B, that I'm going to prove in a minute, doesn't really factor in directly. It's a proof of something we observed a few slides ago. I'm going to present, therefore, more proofs than we need for this. And the reason is because the Kosaraju-Sharir algorithm is not that complicated. That is, it's relatively simple to implement. It's sort of almost below our level as far as implementing it. The issue is exactly why it works is very mysterious. And it's the kind of thing where even making these slides, as somebody who has taught this algorithm multiple times, every single time I have to teach this algorithm, I have to convince myself again why it works. Because it does work. I mean, I have a proof of correctness I'm going to show you, but its mechanism of action is rather mysterious. It's rather obscure. And even once you look at the proof of correctness, you can look at it and say, okay, I agree the algorithm works, but I still don't feel it. It's still weird. It seems like it's almost a coincidence that the algorithm works. And so in the service of providing a thorough justification, I'm going to prove a few more things than I need to. Okay, so the very first one is, let's suppose that we have some strongly connected component called C of a directed graph G. And now suppose that I'm in the middle of a DFS traversal. It doesn't make any difference where I started the DFS traversal. Just suppose that I have this component called C, and there's a vertex U that is the first vertex of the component visited during this traversal. Theorem A states that every vertex in the component must appear as a descendant of vertex U, the first vertex of C visited, in my DFS tree. In other words, basically what I'm saying is if I look at all the other vertices in the component, all of them are going to be descendants of U. There isn't going to be some vertex that appears in my DFS tree as a descendant of something else outside the component. Everything, if U is the first part of the component seen, everything else in the component gets seen before I unwind from U. This is actually a special case of a general property of DFS that we have exploited before, arguably the signature characteristic of DFS, which is that if you arrive at a particular vertex during DFS, before you leave that vertex for the last time, every single vertex reachable from vertex U has already been visited. This is basically just a special case of that. Okay, so here is my proof. It's just a one-slide proof. Before DFS unwinds from a vertex, as I've said, all vertices reachable from that vertex have been visited by that time. Because C is a strongly connected component, well, clearly there has to be a path from U to every other vertex in my component. And since no vertex of my component was visited before vertex U, since I defined vertex U to be the first vertex of C to be visited, that means that all vertices in C must be visited sometime between when I first arrive at vertex U and when I leave vertex U. And the vertices visited between when I arrive at vertex U and when I leave are all going to be the vertices that are the descendants of U in the DFS tree. And therefore, all of the vertices in my component must appear in the subtree rooted at U in my DFS tree. Okay, so there's theorem A. I want to now go right into theorem B, which is a proof of this property I mentioned a few minutes ago that just seems really weird. In fact, I'm going to backtrack to it to show that slide again, because I've said a lot of things in the meantime. So notice how if I generate a DFS tree at vertex A, and then I look at this component here, this far away component that's irrelevant to vertex A, notice how the DFS tree stays inside of the component. That is, although the DFS tree could, for all I know, eventually leave the component later, if I look at any two vertices within the component, the path between those two vertices stays entirely inside of the DFS tree. And that might be a coincidence. That is, for all we know, there could be a DFS tree where the path between, let's say, D and G does something like this. It goes to vertex P, and then it goes and wanders around in the outside world for a while, and then goes back and hits vertex R. There could, for all I know, be a case where if I look at the path between D and G in the DFS tree, that path wanders outside the component before it gets to vertex G. But it actually turns out that that's impossible. It turns out that if I look inside of a component and I consider some DFS tree that reached the component, paths between two vertices in the component will stay inside the component. And that's my theorem B. Okay, so let C be some strongly connected component of a directed graph G. And again, suppose that U is the first vertex of that component that is visited by some DFS traversal. Who cares where the DFS traversal originated? It just comes in from the outside world. The theorem is that the path in the DFS tree from vertex U to any other vertex in the component will only pass through vertices in that component. And like I said a few minutes ago, this is really bizarre to me. Like, I agree that I have a proof. The proof is complete, but it still just doesn't feel right. It seems so strange that DFS is able to do this because DFS doesn't know anything about components. How is it that DFS has this property? Well, however it is the case, that's just a mystery of the universe, it turns out we can prove that this holds. Okay, so here's how we're going to do this. So by theorem A, we know that any vertex in the component is a descendant of U in the DFS tree. So we need theorem A to do this. So I know that U is the first vertex in the component that I saw in my DFS tree, and that every other vertex in the component is therefore some descendant of vertex U. So if I think of the path between vertex U and vertex V in my DFS tree, it is a sort of downwards path in the DFS tree from U to one of its descendants. Okay, so now suppose that path from vertex U to vertex V passes through a vertex called W. Now, this is just a diagram for the sake of illustration, but for the sake of illustration, we don't yet know whether W is inside the component or not. So we'll draw it out here in outer space. And what I'm going to show in a couple of slides is that W has to be inside of this component. I should add, just as an interesting note about writing proofs, well, interesting, depending, I mean, your mileage may vary on that, I actually had this proof typeset as a proof by contradiction. So my original attempt at this proof was, suppose the path passes through a vertex not in the component. And then I was able to write a proof by contradiction. It was a nice proof. But I stared at it and I decided after a while that it wasn't worth using a proof by contradiction. So I'll come back to that point in a minute once we've seen the entire proof. So suppose that the path from U to some other vertex in the component passes through a vertex W. And my goal is to show that W must be inside the component as well. Okay, well, obviously W is reachable from U and V is reachable from W because the path from U to V passes through W. Additionally, because C is a strongly connected component, I know that U has to be reachable from V. There has to be some path from V to U. It can't be the same path that I follow to get from U to V, because obviously that's a directed path. So there has to be some way of getting from V back to U, because that's how strong connectivity works. Now, because reachability is a transitive relationship, so notice how here I don't bother talking about paths, I just talk about the reachability relationship. Because reachability is transitive, that means that U is reachable from W, because I can go from W to V and then from V to U. Okay, but what does that tell us about the status of W? It looks like that means I can get from U to W and from W to U, which means W is in the same component as U and V. Okay, so W is in the component. And so what I've been able to prove here is that if I consider the path from U to any other vertex that I know to be in the component, any vertex that I pass through along the way must also be in the component as well. So therefore, the path from U to V only passes through vertices in the component, and that's my proof. So I mentioned at the beginning that I considered writing this as a proof by contradiction, and we could do this. It wouldn't take, it would only require changing a few lines. Basically what I do is I say, suppose that W is not in the component. And then I get all the way to this step here, and I say that's a contradiction because W is in the component. And then that's the end of my proof. And think about that. Notice how that proof by contradiction was sort of extraneous. I didn't need to have a contradiction there. I could just say, see, W's in the component, so we're good. There's no need to be, I don't know, artificially negative about it. A long time ago, I think in like a second-year algebra course, the instructor gave advice that amounted to, look, you can use proofs by contradiction for lots of things, but don't do it unless you need the contradiction. If you discover that your proof by contradiction can be written as a straightforward, ordinary proof, then get rid of the contradiction. Don't add extra machinery that you don't need. And honestly, that advice clearly has sat with me over the years, and I think it's good advice. I think the purpose of a proof is to communicate, and you don't communicate effectively by confusing people. And people get more confused the more different concepts you have to bring into things. And so it's sort of nice to approach proofs from a sort of minimalist point of view of, you want to say definitely enough to convince somebody, but you don't need to over-convince them. Now, I understand that makes me a bit of a hypocrite because I go through proofs all the time where the proof itself is like 3 lines long and I spend 25 minutes talking about it, but I'm talking about the text of the proof, not necessarily whatever verbiage I put over top of it in a voiceover. Okay, so there's our proof of theorem B. So if a DFS tree gets into a strongly connected component, it rattles around inside the component until it's reached every vertex in the component. There is a path in any DFS tree between vertices inside the same component that passes through only vertices in that component. Okay, now we're ready to talk about the Kosaraju-Sharir algorithm. The algorithm has 2 phases. I'm going to call them phase 1 and phase 2. And in phase 1, we work entirely with the original graph. And in phase 2, we work entirely with the transpose graph. What happens in phase 1 is I run a series of DFS traversals until all vertices are visited. And just like in our earlier connectivity tests, once a vertex is visited by one traversal, it stays visited. So the next traversal does not visit it. And then I keep on the side a stack. And as DFS unwinds from each vertex, I push that vertex onto my stack. So what I'm doing here effectively is pushing the vertices onto the stack in a sort of post-order visit pattern, similar to our topological sorting algorithm from the last lecture. Okay, so although we just do traversals until every vertex is visited, I am going to follow the convention we've been following so far, where I just go through vertices in alphabetical order, and when I find an unvisited one, I run a traversal. So the first one I try is vertex A. I do a traversal at vertex A, and so it looks sort of like this. I go from vertex A to B, B to C, C down to H, there we go, and then I'm ready to unwind from vertex H. When I unwind from vertex H, I push it onto my stack. Okay, so I unwind from vertex H, I get to vertex C, I unwind from that, I push it onto my stack. I get back to vertex B, but I'm not done at vertex B yet. I have to walk down to vertex I and then vertex J. So I push vertex J and then vertex I onto my stack. I end up back at vertex B. I'm now done at vertex B, so I push vertex B. I go back to vertex A, and then I push that on the stack. So you can see the vertices are pushed onto the stack in a sort of post-order of the order DFS visits them, in the order in which DFS unwinds from the vertex. All right, so I then end up with these 6 things on my stack. I go looking for an unvisited vertex, and I think vertex D comes next. There we go. I'll come back to the slide I skipped in a minute. I do a traversal rooted at vertex D, and now my stack looks like this. I push these 4 vertices onto the stack. Okay, so one observation I'll make, once we are familiar with this idea of pushing vertices onto the stack as we unwind, is that I did a traversal at vertex A here, and I traversed all of the things reachable from vertex A. Now, I don't know which of these things are in the same component as A yet, but I do know that only things that I have seen during this traversal can be in the same component as A. That is, whatever component contains A is some subset of these things, the things I just visited. The reason why that's significant is, notice how, if I look at vertex A, all of the things in the same component as A therefore have to have already been visited and therefore must be below A on the stack. That's going to be a key thing that we need in phase 2. All of the vertices in the same component as A are below it on the stack. Alternatively, I guess we can also think about it like, if I go find the first vertex in that component, everything else in the component, of course, has to be below it in the stack. All right, so I then finish off phase 1. I traverse, starting at vertex D, I do another DFS, and then I push those things onto the stack. Okay, so I may have to do several different rounds of DFS in this sort of stop-start fashion that we've seen already during this lecture before I cover every vertex. And during each of these traversals, so when I did a traversal starting at vertex D, notice that I did not go to vertex C, even though there is an edge from D to C, because C had already been visited. So the only vertices that I traverse are vertices that have not already been marked as visited. One of the reasons that that's important is we're going to use that to show that, just like in our previous cases, the set of all traversals together requires linear time. All I'm doing is ensuring that every vertex eventually gets visited. So the first phase of the Kosaraju-Sharir algorithm, every vertex is visited exactly once, and so the total running time of my first phase is linear in the number of vertices and edges. All right, so what's the second phase? In the second phase, I switch over to G transpose, and I mark all vertices as unvisited, and I'm going to do another series of traversals, also visiting all vertices, except this time, I'm not just going to go in an arbitrary order, I'm going to use the stack. I'm going to go down the stack. So I'm going to start, for example, with a traversal at vertex D. The basic rule I'm going to follow is I'll do a traversal at vertex D, so that visits a bunch of stuff. I'm doing the traversal in G transpose. So notice that the diagram on the slides during phase 2 here is going to be G transpose. So I traverse G transpose from D, and I end up reaching, I guess I reach this stuff here. Is that it? That might be it. Okay. In any event, what I'll do is I'll visit certain vertices on my traversal, and then when I need to start off a new traversal, what I will do is go to my stack, and I'll just ignore any vertices. I'll pop them off the stack if they've already been visited. So I just pop vertices until I find a vertex that hasn't been visited, and then I run a traversal starting there. That's the basic pattern of phase 2 of the Kosaraju-Sharir algorithm. Okay, so at the beginning of the second phase, I clear the visited status of every vertex. And then I just pop the stack until I find a vertex that hasn't been visited. So of course, at the beginning of the second phase, nothing has been visited. So the first thing I look at, vertex D, which was at the top of the stack, that is the vertex from which I run my first traversal. Okay, so it looks like my traversal had been correct earlier. I then perform a DFS traversal in G transpose, rooted at vertex D. There it is. And notice how it visits these things. Okay, now here's where something spooky is going to happen. So I look at the set of vertices that I visited, and then that is my component. And as I said earlier, this is one of these algorithms where the machinery of the algorithm is simple, but why the algorithm works is just really weird. Like it's very hard, even if we see the proof of correctness, to fully engage with the idea that, oh yeah, you just do the traversals in this order, and somehow the components just fall right out. You just do a traversal, and whatever you reach, that comprises a single component. So I perform a traversal at whichever vertex I popped off the stack that is unvisited, and then I look at all vertices visited by that traversal, and notice that actually applying our insight from earlier, since D was at the top of the stack and all vertices were below it, obviously it's the case that all vertices in the same component as vertex D are still on the stack as of when I begin this traversal. It actually turns out, so I'm going to need that in the proof of correctness. And so then it turns out if I just take all the vertices I visited, that is now one strongly connected component. Now I'm not done yet because I have to traverse all the other vertices. I'm going to leave these marked as visited. I'm not going to see them again. So if for example I'm doing a traversal at vertex C later, I do not follow this edge because the other end of the edge is a visited vertex. I treat that vertex as if it's already been visited. I never see it again. Okay, so I've now wrapped up one strongly connected component. So I'm going to go looking for a vertex to start my next traversal. So I go to the stack, I cross off E, I just pop it off the stack because E has been visited. I pop F, I pop G, and that brings me to vertex A. Okay, so I'm going to do a traversal rooted at vertex A. All right, I do the traversal, and then these are the vertices that I reach. Okay, and that's going to be my next component. So notice that vertices that had already been visited during the second phase, so for example, the ones over here, those are going to be ignored by my traversal. So although my traversal does go from A to J, from J to I, and from I up to B, when I'm at vertex B, I'm not allowed to follow this edge because at the other end of the edge is something that's already visited. And so what that tells me is the set of things visited by this traversal, the ones that are part of this traversal tree, are just these four vertices, and that's my next component. So the general rule in the second phase is you do a traversal, the set of vertices that are part of that traversal tree are together one complete, strongly connected component. And maybe this second component does give us a hint as to exactly how the magic is happening in the algorithm. So there is a way to get from vertex B to vertex D, but fortunately we didn't include vertex D in our component because I happened to deal with it first. So earlier in phase 2, I already locked down these vertices as being in a component. Similarly, I didn't cross the bridge from vertex I to vertex G because it was already locked down. So I guess the trick that the algorithm is using is it's somehow by pushing things onto the stack in the order it did, it was able to ensure that components on the way back during the second phase get visited in a certain order so that each component gets locked down before any other component that feeds into it could cross the bridge and pull in vertices. Because we can see if we had started with a traversal of vertex A and we hadn't visited all these things in advance, we might have pulled in vertex D and vertex G, maybe even vertex F and vertex E into the component containing A, which it doesn't belong over there because although there's a bridge between this component and the one to its right, there are no bridges in the opposite direction. All right, after we're done that, the next unvisited vertex on the stack, so once I've finished with the component containing A, and I pop everything in that component off. The next one is vertex C, so I do a traversal at vertex C. I don't visit any already visited vertices, and I pull in vertex H as the other vertex in that component. And we can see now if I keep popping things, eventually the stack is going to be empty, and that means I have visited all vertices. And what I did during phase 2 was basically just another round of like a complete DFS of the graph. I make sure every vertex gets visited once. I do a bit of bookkeeping, which is I do compile a list of all the vertices that I see during my traversal to wrap that up into a component. But ultimately, I am just doing basically one full DFS of the graph. And so the running time is again this. My phase 1 running time was also this, and so my total running time is just 2 times the number of vertices plus the number of edges, or asymptotically 2 times that, so 2 times some constant times that, which means the Kosaraju-Sharir algorithm is linear. And so our winning streak continues. I don't know that we can expect it to go on for much longer, but we made it through this entire lecture without ever having to settle on an algorithm that was worse than linear time. All of the graph theoretic properties we've needed so far in this entire course, we've been able to compute in linear time. Okay, so I've now found the strongly connected components of this graph. Or have I? I mean, I guess I haven't given a proof yet, but we'll start by showing the pseudocode for the process that I just followed. So here is the pseudocode. It's a bit bulky, but only because I have to have 2 phases. So I make a list to store my components. In this example, I'm just going to represent my components as sets. So a component consists of a set of vertices. I create a stack, and then I begin phase 1. So I mark every vertex as unvisited. I just loop through all vertices and then look for unvisited ones. If I find a vertex that is unvisited, I run a DFS traversal rooted at that vertex. I didn't bother with a pseudocode for that because we know what DFS is by now. And then when DFS unwinds from a vertex, so at the post-order step, during the post-order visit of DFS, I push the vertex onto S. This is, the DFS I would use for this step would be very similar to the one I used for topological sorting at the end of the last lecture. structure. Okay, so once phase 1 is over, I enter phase 2. In phase 2, I mark all vertices unvisited again, and then instead of just iterating through vertices, I walk through the stack. It's easy to justify that the stack will have size at most n because I only visit each vertex in my phase 1 DFS once, and I push each vertex onto the stack only once during that visit, so the stack itself can contain at most n vertices. During phase 2, as long as the stack is non-empty, pop the first vertex. If that vertex has already been visited, then just do nothing and keep going. If it is unvisited in phase 2, then do a DFS rooted at that vertex in G transpose, figure out the set of vertices that were discovered by that traversal, that were visited by that traversal, and then add that as our next component. And that's the Kosaraju-Sharir algorithm. All we have left to do is to prove that it works. So I have two theorems for that, Theorem C and Theorem D. The two theorems together comprise a proof of correctness. Basically, the way I'm going to do this is I'm going to talk about these traversals we did in the second phase. So what I want to show, the fundamental action of the algorithm is I do a traversal in the second phase. I take the set of all things that I visited during that traversal and I say that is a component. So what I want to prove is that that actually is the case, that the set of things visited by each traversal during the second phase is one complete, strongly connected component. I'm going to prove that with two different results. The first result is that if I do the traversal, everything I see is in the same component as my starting point. So all the vertices I visit are vertices that are supposed to be part of the component. Okay, that's one half of what I need. The second theorem has to be that every vertex in the component gets visited. So it's not enough just to say that all the vertices I visit are in the component, because what if I only visited these vertices here? I also have to prove that I visit every vertex in the component. So I don't visit any vertices outside the component, and I do visit every vertex inside the component. So the first step is I'm going to prove that every vertex I visited is in the same component as the vertex I started with. That's Theorem C. Okay, so I've drawn some diagrams for this proof, up to the point that I actually went back at the last minute and expanded the proof out over several slides because I felt like it was impossible to describe it without diagrams. The diagrams themselves are a little bit of a hassle anyway because we're talking about both G and G transpose during these proofs, and it's really hard to do that with illustrations. So what I've decided to do is, in all of my diagrams, the situation depicted by the diagram is the original graph G. This is true even though I understand in phase 2 we're doing traversals on G transpose. So in the original graph G, if I do a traversal rooted at vertex U in G transpose, the paths that I find in that are going to be paths from other vertices to U. Because in the original graph G, if I take my traversal of G transpose and map it back onto my original graph G, I'm finding inbound reachability. So you'll discover that the direction of paths in my diagrams doesn't seem to match up with the direction of things in G transpose. That is deliberate because the diagrams depict the original graph G. I tried having the diagrams depict G transpose, but it was equally as confusing. So if both options are equally as confusing, better just to stick with the non-transposed version. All right, so the proof of Theorem C, and just a reminder, Theorem C is that when I do a traversal in phase 2, every vertex I visit is in the same component as my starting point. All right, so the only vertices that can be visited by the traversal rooted at U in G transpose are vertices that have not yet been visited in the second phase. That I don't think is very controversial. And that means the vertices that I visit, if I do my traversal rooted at U, have to still be on the stack. Now, to be clear, if I look at my stack here, so here's my stack, and I've got some vertex U. U is at the top of the stack, and so I decide to do a traversal rooted at U, okay? There are other vertices also on the stack. Now, what I'm claiming is that all of the vertices I visit in this traversal have to still be on the stack. I am not claiming that every vertex on the stack is unvisited. There could be vertices on the stack that have already been visited. That's fine. What I'm saying in this line is that all the vertices I visit must still be on the stack. So the ones that I see, all of the unvisited vertices have to still be on the stack. All right, so let V be a vertex visited by the traversal rooted at U in G transpose. So I do a traversal in G transpose rooted at U. This diagram, remember, depicts the original graph G, and I get during that traversal down to vertex V, which means what I've discovered, if I'm traversing G transpose, what I've discovered when I find V during that traversal is in that DFS tree I have a path in the original graph from my vertex V back to my vertex U. So suppose that U is a vertex visited by by this traversal. And what I want to prove with theorem C is that this vertex must be in the component. That's what I'm trying to prove. So for the sake of a contradiction, suppose that the vertex I discovered is not in the same component as my starting point. Okay, so what do I know? Well, what I know is that V is reachable from U in G transpose, which is to say there is a path from V to U in G. Okay, but I've just said that V is not in the same component as U. V is in some other component. So because I can get from V to U, the only way they can be in different components is if there is no path from U to V in my original graph G. There cannot exist a UV path in my original graph G. All right, so V has to appear below U on the stack. And here's how I know that. When I started my traversal at vertex U is at the top of the stack. And I visited vertex V, which means vertex V was unvisited when I began my traversal at U. As I said earlier, the only times a vertex can be unvisited is if it's still on the stack, which means if vertex U is the top of the stack, vertex V has to be somewhere below vertex U in the stack. Okay, that's why I'm claiming here that vertex V appears below U in the stack. Okay, so what does it mean? I'll keep that up there, but what does it mean when I have a vertex V below vertex U in the stack? Well, things were put in the stack during the first phase. So let's go back to the first phase. We'll go back in time and think about what happened during the first phase. In the first phase, I pushed vertex V onto the stack before I pushed vertex U. So what that has to mean is either that I completely finished with vertex V before I even touched vertex U, or alternatively, that I was still recursing from vertex U when I got to vertex V. That is, maybe vertex V is a descendant of vertex U in the first phase DFS. But in any event, I finished at vertex V and unwound from it before I unwound from vertex U. Now, I know that there is no path from vertex U to vertex V. So on the previous slide, we said there is no path from vertex U to vertex V. What does that tell us about when vertex V was visited in the first phase? Well, it means that clearly if there's no path from vertex U to vertex V, then at the time that vertex V was visited, it was not visited as a descendant of vertex U. Because if it was, there would be a path and that would be a contradiction, okay? That means that vertex V was visited from some other direction. Somebody else visited vertex V during my first phase. Okay, so what that has to tell us is that I unwound from vertex V before I'd even seen vertex U, because vertex V is not a descendant of vertex U, which means vertex U is completely unvisited. Nobody had ever seen it before at the time that I first unwound from vertex V in the first phase. Okay, so I came to vertex, I'm going to clear my diagram up a little bit here. There's lots of arrows getting in the way. In the first phase, I arrived at vertex V from some other direction, and then I unwound from vertex V and I pushed V onto the stack. Okay, and then sometime later, I reached vertex U. And so that means vertex U was fully unvisited at the time that I unwound from vertex V. This is a contradiction, though, because we saw earlier that there is a way in my original graph G to get from vertex V to vertex U. And I just said that because we know that vertex V wasn't a descendant of vertex U, that means that when DFS reached vertex V in the first phase, vertex U was unvisited. But we know that vertex U is reachable from vertex V, and that's a contradiction, because we know that DFS would never unwind from vertex V until after vertex U was visited. And that's a contradiction of the same insight behind theorem A. But in any event, it's a contradiction. Vertex U, if it was fully unvisited when vertex V was encountered, would have been visited as part of the traversal of vertex V. But it wasn't, because we saw that vertex U was on the stack above vertex V. That's a contradiction, and so we'll go backwards and try and figure out what caused the contradiction. Where did I make an assumption that resulted in a contradiction? And it turns out it's way back at the beginning of our proof. It is, let's see, right here. Suppose that vertex V is not in the same strongly connected component as vertex U. But we tried that, and if we make that assumption, then something impossible happens. We get a contradiction. Therefore, this has to be false. This can never occur, which means that if vertex V is a vertex visited by the traversal rooted at vertex U, then vertex V must be in the same component as vertex U. And that is what we are trying to prove with theorem C, that every vertex I visit in the traversal is in the same component as vertex U. So by contradiction, we have shown that to be the case. All right, so we have theorem C. Theorem C tells us that if I start at a particular starting point in phase 2 of the algorithm, every single vertex I visit is part of the same component as my starting point. All I need to bring this across the finish line is theorem D, which is that every vertex in the component gets visited. Because all theorem C assures us of is that if I visit a bunch of vertices, they're all in the component. It doesn't guarantee me that I visit everything in the component. So that's the last step, the keystone in the arch. So theorem D. In the second phase, if U is the current vertex, if it is the thing that I am the root of my current traversal, then every vertex in the same component as U, we'll try that underline again, every vertex in the same component as U must be visited by the traversal I perform at vertex U in G transpose. All right, we're almost there. Okay, so we already know, obviously, that if I do a traversal, so if I start at vertex U and I do a traversal in G transpose in general, so if I don't consider whether vertices are already visited, I start with a brand new copy of G transpose, we already know from way earlier in this lecture, like an hour ago, we know that if I do a traversal starting at vertex U in G transpose, I will visit every vertex in the same component. That is definitely going to happen. What I have to show in this context is that if in the middle of the Kosaraju-Sharir algorithm, I start a traversal at vertex U, there is no way that some vertex in the component has already been visited. That's actually all I have to show, because we know that if I do a traversal in G transpose, starting at vertex U, I will see every vertex in the same component as vertex U. All I have to assure is that none of those vertices have already been captured. None of those vertices have been visited by somebody else. So that's really the only proof I have to write. All I have to show is that no vertex in the same component was already visited before the traversal rooted at vertex U was performed. Because obviously, if V had already been visited, it would be ignored in the traversal from vertex U. That would be a case sort of like this. Look at vertex D here. If I do a traversal at vertex A, I never go to vertex D because it gets ignored since vertex D was already visited. So all I have to show is that if there is a vertex in the same component as vertex U, that vertex cannot already have been visited by phase 2 at the moment when I start my traversal from vertex U. All right, so suppose that, so we're going to go for a contradiction again. Suppose that some vertex V in the same component as vertex U had already been visited in the second phase before the traversal at vertex U was started. Well, obviously what that means is that there was some other vertex, so this diagram depicts my original graph G. That means that there was some other vertex in the second phase, we'll call it vertex R, where I did a traversal beginning at vertex R, and that traversal visited vertex V. Now the path points towards R because the traversal I did was in G transpose. So the path that I found was a path from V to R. So my goal is to find a contradiction here somewhere. I'll tell you what the contradiction is going to be. The contradiction is going to be that I'm going to show that basically vertex U was already visited, which means I never needed to do a traversal at vertex U. That's the contradiction I'm actually going for. Because the theorem was, if I do a traversal at vertex U, I visit everything in the component. I'm going to show that either that's true, or I didn't need a traversal from vertex U to begin with. Okay, so by theorem C, when I did a traversal rooted at vertex R earlier in phase 2, I reached vertex V. But remember that theorem C told me that everything I reach from this traversal must be in the same component as my starting point. So that means that vertex R and vertex V are in the same component as each other. Okay, fair enough. Let's see where that takes us. Because vertex R and vertex V are in the same component, it is reasonable to conclude, since I already declared that vertex V is in the same component as vertex U, that vertex U, vertex V, and vertex R are all in the same component as each other. All right, so at the time that the traversal from vertex R was started, both vertex U and vertex V, they were both unvisited. And the reason I know that is, at this state in the future, where I'm about to start a traversal on vertex U, obviously vertex U is unvisited. How would I start a traversal on it if it were already visited? And vertex V got visited by the traversal from vertex R. So in the past, when I started my traversal from vertex R, both vertex V and vertex U had to have been unvisited. But that's a problem, because since vertex U and vertex V are in the same component, I would expect that the traversal from vertex R would have visited vertex U. Therefore, vertex u would already have been visited by the time it was on the top of the stack. So the whole point of theorem D here is, suppose vertex u is on the top of the stack, and I decide to do a traversal starting at vertex u because it's unvisited. Well, none of that makes sense if vertex u has already been visited. And because I could show that when I do a traversal from vertex r, since at the time I did that traversal, vertex u was unvisited, we know that any traversal in G transpose from vertex r will reach all unvisited vertices in the same component as vertex r. Therefore, vertex u was visited, and that's a contradiction because we began our proof by assuming vertex u was unvisited, and we were about to perform a traversal starting there. Great, we've got our contradiction. So we work our way backwards and try and figure out where the problem was. The problem was this. It was, suppose there is some vertex in the component that was already visited before I started my traversal at vertex u. This assumption got us into all kinds of trouble, and we found that because a contradiction occurred, this is impossible. And therefore, if I begin a traversal at vertex u, I'll erase that horrible mangling of the word impossible there. If I begin a traversal at vertex u, I can assume that all of the other vertices in the same component as vertex u are not yet visited. And therefore, of the vertices I reach in my traversal, of which all of them are guaranteed to be in the same component, I can assume that I do indeed reach every vertex in the component because all of them would have been unvisited. And I know that in the DFS tree I start at vertex u, basically by theorem B, the paths to all the other vertices in the component must run only through the component. So there is no way that a vertex can be stranded. A vertex in the component, which I now know is unvisited, can be stranded in such a way that it's not reached by a traversal from vertex u. So my contradiction proves theorem D for me, and that tells me that the traversal rooted at vertex u in the second phase will visit every vertex in the same strongly connected component as vertex u. Okay, so theorem C tells us that the traversal rooted at vertex u in the second phase, when a vertex comes up at the top of the stack and it's unvisited, the traversal I do at that vertex only visits things in the same component as my starting point. Theorem D tells me it visits everything in the same component as my starting point, and therefore, when the Kosaraju-Sharir algorithm takes everything visited by that traversal, batches it all up and says that is one strongly connected component, it is correct. And therefore, the algorithm correctly computes the strongly connected components of the input graph G. Great! How do you enjoy the world of intermediate graph algorithms? Not only do we get to name things after people, we get to spend half an hour picking our way through proofs of correctness of properties that are still rather mystifying. Like, even having written those proofs, I agree that the algorithm works, but I don't quite feel it. It still doesn't feel like the algorithm can work. It feels like the properties it's leveraging are sort of magic. But no matter. That's the way math works. We have a proof. We know the property holds. Sometimes proofs just aren't very satisfying. All right, we need something to cool down on before we end the lecture. I want to go back to this observation about the relationships between strongly connected components. So notice how, if we look at this graph we've been looking at for the entire lecture, there are edges between strongly connected components. But of course, we also know that although it's possible to go from component A into component B, we'll never have a bridge going in the opposite direction, because if we did, that would mean we just have one big component after all. And that implies that there's a sort of hierarchy to our components. So, for example, if I just erase all the vertices and label components with numbers, so there's component C0 and there's component C1, we can observe the relationships between different components. In fact, I could go further. I could take this visualization and I could collapse down. I could compact each of my components into a vertex. And if I have multiple edges, notice how there are two edges connecting C4 to C3. What we'll do is just collapse them down into a single edge. I end up with this thing. We call this thing a reduced graph. The reduced graph of a directed graph G is the result of taking each of its strongly connected components, which we now know how to identify in linear time, and compacting them down into one vertex. And then if there's multiple edges between components, so for example, C4 and C3 have these two edges, we collapse those into a single edge, like this. So we end up with a valid, simple directed graph. We call this thing the reduced graph, and it has a vertex corresponding to each connected component of the original graph. And something interesting to think about, so an observation that I just made was that there can be an edge going from C4 to C3, or there could be an edge going from C3 to C4, but there can never be both, because if there were, that would imply we have one big component. In a sense, what that's sort of telling me is that the graph doesn't have cycles. And so I'll leave you with that exercise. Prove that the reduced graph of any directed graph G is a directed acyclic graph. And I like this because it gives us a nice way of linking together the types of graphs we've been talking about over the last 2 lectures. We spent the last lecture talking about directed acyclic graphs, which are graphs where the strongly connected components are pretty boring. That is, each component contains only one thing. And we spent this graph talking about, this lecture talking about strong connectivity, and we can now see there is this transformation that takes any directed graph, whether or not it contains cycles, and condenses it down into a directed acyclic graph. All right, where do we go from here? Well, we are firmly in the world of intermediate graph algorithms, and we've got a pretty big set of algorithms coming up. There's one problem for which I want to describe 3 sort of equivalent but still quite unique algorithms. But before we get there, we have to talk about another data structure for a change. We have to take a break from graphs and go back to the world of data structures, which we're going to do in the next lecture.